Hello students, welcome to our video lecture on cutting temperature. This is a part of the course Machine Tools and Machining. This course is currently taught by 4 teachers, me, Nilanjan Chakladar, Professor Sankha, Professor Soumitra and Professor Partha Pratim Bandyopadhyay of Mechanical Engineering Department at IIT Kharagpur. This lecture is targeted primarily for higher undergraduates. The lecture is divided into multiple 15-minute snippets for you to take breaks in between. If you are learning this lecture alone, we recommend you take notes from the beginning and write down your queries during the break. If you are learning this lecture in a group, discuss and accumulate your queries during the break. The stock layout consists of heat sources in machining, temperatures in machining, estimation of shear zone temperature, numerical problem, effects of process parameters and tool geometry on average cutting temperature, temperature control in machining, and temperature measurements. Now there is a table of learner's time, so how much time you should spend on each section. Heat sources in machining. There are 3 possible zones where heat is generated, denoted in the figure by 1, 2 and 3. 1 is the primary shear zone, 2 is the secondary shear zone and 3 is the work tool interface, particularly in case of blunt or worn tool. The heat apportionment is to be understood now. While the chip flows across the shear plane, majority of the heat is taken away by the chip. Some is left over into the workpiece. In the zone 2 at the chip tool interface, majority of the heat is again taken away by the chip and some penetrates into the tool. In case of a worn tool, due to friction with the machined surface, majority of the heat is absorbed by the machined surface and some heat is taken up by the tool. So zone 1, heat in the shear zone is responsible for the rate of energy with which the chip shears, that is PS times Vs. Zone 2, heat at the chip tool interface is due to the rate of energy spent in the friction of the chip relative to the tool, that is F times Vf, and is very much affected by the thermal properties of the work material and the tool material. The third zone, also called as the flank wear land, for a tool which has some wear, the source of heat generation is responsible for the rate of energy due to friction between the worn tool and the machined surface. In this case, it is F flank, that is an additional force along PZ due to development of flank wear. So F flank times Vc, and this gives the total machining power PZVC plus PXV feet. PXV feet is usually orders smaller than PZVC, so we can say the total machining power is PZ times VC. PZVC can further be expressed as a sum of PSVS plus F times VF. Therefore, PSVS equals to PZVC minus F times Vf equals to rate of heat generation at the shear plane. So what measures can we take to protect the tool from heat penetrating into it? A protective coating of alumina is put on a tungsten carbide tool so that heat cannot enter the tool, as the alumina acts as a thermal insulator. So heat apportionment is dependent on the thermal conductivity of the tool and the material. Coming to temperatures in machining, theta ambient is the ambient temperature, theta shear is the shear zone temperature, theta chip is the chip temperature, theta chip tool is the chip tool interface temperature, the average chip tool interface temperature, theta tool is the tool temperature, and theta workpiece is the temperature of the machined surface. If the workpiece temperature increases, there is an expansion in the workpiece, the thermal expansion in the workpiece, leading to poor dimensional tolerance. If the average shear zone temperature increases, there is a reduction in the shear yield strength, less is the cutting force required, and it is suitable for hot machining. Theta workpiece is higher for thin walled jobs and very high for hard turning. So what do we mean by hard turning? Jobs harder than 45 HRC, such as 4320 steel and 1050 steel operations. As average chip tool interface temperature increases, tool wear also increases, and that finally reduces the tool life. So average chip tool interface temperature affects the formation of built-up edge as well as it affects the tool wear phenomenon. So let us take a 5-minute break. Note down your queries. Please think about the concepts which we have already discussed and resume the session once you are ready. We now begin estimation of shear zone temperature in machining. We already mentioned that the rate of heat generation at the shear zone is responsible for the term PS times Vs. Now let us write down the heat balance equation, that is heat absorbed is equal to the heat released. This is the mass flow rate across the shear zone times specific heat times the rise in temperature, which is equal to the rate of heat taken away by the chip. A1 times B times Vc, this gives the volume flow rate. This volume flow rate times the density gives the mass flow rate. This mass flow rate times the specific heat times the temperature rise gives the total amount of heat absorbed. This is equals to eta times PS Vs 1 minus capital gamma. So what is eta and what is capital gamma? Eta is the percent energy taken away by the chip, which can be 90 to 95%, and rest goes into being residual stress. Gamma, the capital gamma, is the amount of heat transferred to the workpiece. Now let us solve a problem. Capital C, which is the machining constant, is equals to 85 degrees. F over N, that is the frictional force over the normal force, equals to 0.5. Gamma O equals to plus 10 degrees. Tau S, the shear yield strength, is 500 megapascals. T is equals to 4 millimeters. S is 0.25 millimeter per revolution. Cw, that is the specific heat, is 500 joule per kgk, that is of the workpiece. Kw, that is the conductivity, the thermal conductivity, 50 watt per meter Kelvin. Then rho W, 7800 kg per meter cube. Eta equals to 0.95. Vc equals to 3 meter per second, and assuming 90% of the heat enters the chip from the primary shear zone. So estimate the shear zone temperature if theta ambient is 30 degrees Celsius. So eta equals to tan inverse of F over N, which we already know, that is the eta angle, the friction angle becomes 26.57 degrees. Now as we know the machining constant, we can use this expression 2 beta naught plus eta minus gamma naught equals to C, where beta O equals to 34.215 degrees. Now Pz is Ts tau s divided by sine beta O times cos of eta minus gamma O divided by cos of eta minus gamma plus beta. So this we get from the Marchant circle diagram. This gives Pz equals to 1348.05 Newton. Ps, Ts tau s by sine beta O, that is 889.21 Newton. And using the sine rule of a triangle, we get Vc over cos of beta minus gamma equals to Vs over cos of gamma O. This gives Vs as 3.24 meter per second. So if we use the heat balance equation, which we have already derived, we get theta s, which is the only unknown here. So theta s is equals to 210.54 degrees Celsius. So shear zone temperature, so to find out the total shear zone temperature, we need to add the ambient temperature. That gives 240.54 degree Celsius. So our question was originally what is the shear zone temperature? The shear zone temperature at an ambient of 30 degrees Celsius is 240.54 degrees Celsius. Let us take a break and try to think about the numerical problem we just explained. So what happens if we use a brittle material? How the shear zone temperature would change? What are the parameters that would affect if it was a brittle material? Coming to the effects of process parameters and tool geometry on average cutting temperature. So first let us introduce some terms. Ks, which is equal to Pz by Ts, is called the specific cutting force, that is expressed in Newton per millimeter square. Qs dot equals to Pz by Ts. T stands for, as usual, the depth of cut, and S is the feet per revolution. So Pz over Ts equals to specific cutting heat flux due to the projected contact area and expressed in terms of watt per millimeter square. Again, Qs dot can be expressed as Pzvc over Bcn. So B is the width and Cn is the natural contact length. This is equal to specific cutting heat flux due to the actual contact area, which is again expressed as watt per millimeter square. Now let us look into the effect of some machining process parameters. To begin with, we start with cutting velocity. So as Vc increases, Pz decreases a little. The product Pz and Pz times Vc increases. This is responsible for the increase in average cutting temperature. Also, the specific cutting heat flux increases because Pz Vc over Ts. Here Ts has no dependence on Vc. Again, as Vc increases, Cn reduces a little, that is the natural contact length reduces a little. The product B times Cn also reduces a little. So Pzvc by Bcn increases. Why? Because the numerator increases at a faster rate compared to the denominator. So this again increases the average cutting temperature. Now coming to the effects of S or the feet, here Vc, the effects of Vc we have already seen, but it has been shown here again to give a comparison between Vc and S. So as S or the feet increases, Pz increases a little. So the product Pz times Vc also has a little increase. As a result, the average cutting temperature has a lower increase compared to the effect due to cutting velocity. Now B times Cn also increases a little due to an increase in feet, and Pzvc by Bcn also increases. Now coming to the tool geometry parameters. So effects of phi, or the principal cutting edge angle, on average cutting temperature. The principal cutting edge angle has an effect on the average cutting edge temperature. How? More heat is conducted to the tool and workpiece due to more contact area. Now we can see two figures on the left. The top one has a PCEA or phi equals to 90 degrees, whereas the bottom has phi equals to 45 degrees. Clearly, the top one has a contact area of T times S, whereas the bottom will have T over sine 45 times S, which is greater than the contact area, which is seen at phi equals to 90 degrees. So this means if PCEA is less, that is the principal cutting edge angle is less, more heat is conducted away from the tool. Hence, the average cutting temperature reduces. Now coming to the effects of gamma O, the orthogonal rake. So the tool rake angle is also found to contribute to the average cutting temperature. As gamma O increases from negative to positive and higher positive values, less heat is dissipated to the tool, leading to a reduction in average cutting temperature. Now let us see how we can control the temperature in machining. We have already seen the heat balance equation. in case of dry machining, or as the name suggests, there is no application of cutting fluids or lubricants in any form. So we can write the temperature of the shear zone in dry machining as theta s dry, which is equals to eta times ps vs 1 minus capital gamma divided by the rate of heat absorbed by the uncut chip, that is A1 times B times Vc times rho W times the specific heat capacity. Now temperature is controlled by cutting fluid. So what does this cutting fluid do? So it lubricates, it cools, protects the machine surface and helps cleaning and easy removal of chips. That means the cutting fluid has 4 advantages or 4 features. Now to rewrite the equation, to rewrite the heat balance equation for wet machining, we only add one term, the A star. So if you can see here in the numerator, there is an A star, which is the amount of heat after some heat is taken away by the coolant, and it depends on the specific heat, conductivity and velocity flow rate of the fluid that comes from the boundary layer thickness of the fluid. Let us take a break and try to understand the effects of process parameters. So when we say it is increasing, is it linearly increasing, non-linearly increasing, would it saturate? Then how you could control the temperature in machining, what could be the different forms of lubricant that can be applied to the machining. So try to think on these. Temperature measurements in machining. So until now we have seen how heat is generated at different zones or interfaces, how the temperatures can be calculated and controlled, what are the parameters that affect the average cutting temperature. Now we will learn the measurement techniques of temperature during machining. Particularly we will focus on the thermocouple and the photography techniques. One of the popular method used is the tool work thermocouple technique. As the name suggests, this method uses thermocouple to measure the relative temperature at the junctions in terms of voltage that are expressed in millivolts. Two dissimilar metals but electrically conductive are used in this method, which forms a hot junction and a relatively cold junction, so that the difference can register a change in the voltage, or also called as thermo EMF, which is further calibrated against temperature values. In the figure, we see a turning setup which is adopted to perform the tool work thermocouple technique. The interface between the chuck and the work material, the boundary of the tool post, interface between the work and the tailstock are electrically insulated to avoid electrical conduction and short circuiting of the setup. A rod of same material as that of the tool is connected to the insert, which in turn is connected to the millivoltmeter circuit. Additional rod is kept so that the increase of temperature at the hot junction does not affect the temperature of the insert, work material and tool of dissimilar materials. The technique can only be used when work and tool materials are electrically conductive and they produce significant or measurable thermo EMF, which we have just mentioned. It can measure average cutting zone temperature, and it is a fast and reliable technique. Now the next measurement technique is embedded thermocouple technique. As the name calls, a thermocouple is embedded either on the tool or on the work material for direct measurement of the cutting temperature. It is expected the thermocouple would be kept closer to the junction of the tool and the work material, as close as possible to get accurate measurements. If the thermocouple is embedded inside the insert, then a hole is to be drilled. Now it is very difficult to drill a hole into an insert. So EDM hole drilling may be used, and this technique is particularly used if the millivolt is not very high. The last technique is the IR camera photography technique, which you can see on the bottom right figure. A cutting tool is being fed in the transverse direction. There is an IR camera which has a high megapixel and high frame rate. This photograph, which you get as fringes, or also called as isotherm lines, which you find on the bottom left, in this case each line maintains the same temperature. So this method, IR camera photography technique, is widely used where we are interested to get series of isotherms over a period of machining time. Now with this we conclude our lecture on cutting temperature. Learners are recommended to read the following textbook, Machining and Machine Tools by Professor A.B. Chattopadhyay, the chapter for the chapter Cutting Temperature, and these are the detailed articles and sections which you are recommended to study. Thank you for listening to the lecture. We welcome any queries you may have on this lecture series. Thank you.